In this video, we're given two functions f and g, and we want to find the domain of the composite function of f with g. Now for the regular domain of f, for a rational function, we look at the denominator and we restrict any number that makes the denominator 0, because you can't divide by 0. It's undefined. So for the first function, the domain is all numbers x not equal to 1. So everything except 1. We want to find the domain for function g. We simply look at the denominator and eliminate any number that makes the denominator 0. In this case, it's x, so x cannot be 0. That's all the domain is. A set of all numbers that are permissible replacements for x in each function. Now for the composite function, the domain is a little bit different, but it still would depend on the domain of the given functions. So the definition here, we have given two functions f and g, the composite function denoted by f circle g is defined by f circle g of x, which can be written as f of g of x. And the domain of the composite function f circle g is a set of all numbers x in the domain of g, such that g of x is in the domain of f. So it's a set of all numbers x in the domain of g, such that g of x, that is the range of the function g, has to be contained in the domain of f. So we go back up here then. We can say the domain of f is a set of all numbers x such that x is not equal to 1. That's what you would give if they asked you for the domain of f. We could also use interval notation. We could also use interval notation here and say it's everything from negative infinity to 1, but not including 1, union with everything larger than 1. So that would do from 1 to infinity. So you can give the domain in set builder notation here, set form, but you can give it in interval notation. Now for the domain of g, again, it's the rational function. We simply look at the denominator, got 2 over x. So we want to restrict any number that makes the denominator 0. Well, in this case, it's x equals 0. So simply say it's a set of all x such that x is not equal to 0. Here they're asking for the domain of the composite function. So let's go ahead and find the composite function. We write it this way. F circle g can be written this way, and this can be written in turn f of g of x. Instead of evaluating the function at a certain number, we're evaluating the function at the function g. So we have this then is equal to, so f composed of g, we simply take the f function. Wherever you have an x, you put whatever g is. So this will be 3 over x minus 1. So in this case, it's 2 over x, 2 over x minus 1. And we simplify this, multiply through by x. That'll give me a 3x in the numerator. Multiplying by x in the denominator, the x cancels here, I get 2. And then 2 minus x. 2 minus x. So here they're just asking for the domain. But you really have to look at what is the domain of f. What is the domain of g? And then just to double check it, find the composite function. That's this right here. So for the domain of the composite function, and I'm going to give the answer in terms of set builder notation. So it's a set of all x, and we know that x cannot be 0 because its domain of the composite function is all x in the domain of G. So what's the domain of G? Well, everything not including 0. So we can just say, okay, x not equal to 0. So the domain, again, of the composite function is a set of all x in the domain of G. So we know for sure we have to eliminate the x equal to 0. X cannot be 0. And then we have to guarantee then that 2 of x, g of x, is in the domain of f. So that simply means that 2 over x, the domain of f is, again, it's everything except 1. So 2 of x is not equal to 1. Because 1 is not in the domain of f. Multiply through by x here, we get 2, then cannot be equal to x. So the other restriction is that x cannot be 2. So the domain of the composition function, or the domain of the composite function of f with g, is all real numbers except 0 and 2. X cannot be 0. X cannot be 2. This is your domain for the composite function of f with g. Thanks for watching. We'll see you next time.